problem is to determine the minimum required diameter D, rounded to the nearest 1/4 inch for bar AB, given that the allowable stress is 10 KSI. So first of all, you can find this length right here, which is 12 squared plus 16 squared equals that length, which we got 20 feet. And then here we can, we have A, B, and C, and then we have to draw the forces in our free body diagram. So we can do AY here, AX here, CX, and then AY, CY. And then, so here's our main free body diagram. So first of all, we can isolate this B right here and make cuts, right? So here we have this force, this sideways force, and this this diagonal force going down here, and then we have our 24 kip force. So this right here is force BC, and then this is force AB. So that's because this is going to be the A and this is going to be the C, right? So, and this is point B. So with this, we can make our equilibrium equations. So we can start by doing our forces, or our y forces, so that would equal 0. So we have our upward force here, 24 kips. So we have positive 24 kips. And then we have our diagonal force, F of AB, or force of AB. So for that, we'd have to do like using sine and cosine. So in this case, because it's this vertical force right here, we're going to be using sine. So this would be, or because we have our upward 24 kip force here, this y force would probably be negative for equilibrium. So we're going to do negative force AB, and then this would be sine. So sine theta. So we have our lanes here, so we can use that to find like what sine is. So if we have this here, this is 12 feet, this is 16 feet, and this is 20 feet. So for sine, that would be SOHCAHTOA, opposite of hypotenuse, equals 0. So then we have 24 kip minus FAB, and then sine, which is opposite over hypotenuse, that would be 12 over 20. So 12 feet over 20 feet, right, equals 0. So this would be FAB is equal to 24 kips over 12 over 20, which is 40 kips. So FAB is equal to 40 kip. So that's an important value because that's the normal force for when we cut like AB, right? So if we drew a free body diagram, this is B and this is like a cut, we have our normal force, which is FAB. AB, which equals 40 kip. So now we have what we need to find the original equation, which is solving for the diameter using the allowable stress. So if I do it right here, stress is equal to the normal force over area. So we have our stress, which is 10 KSI, and we have our normal force, FAB, which is 40 kip. And then we don't have the diameter for the area, which is what we're looking for. So we're going to use these two to find our missing variable, right? So allowable stress, that is 10 KSI. So I can put 10 KSI is equal to our normal force, FAB, which is 40 kip. And then our area, which would be pi over 4 times diameter squared. And then because KSI is kips over inches squared, we have kips here, so now we can put inches. So inches squared. And then we would isolate D to find like our missing diameter. So when we solve for D, we get D is equal to 2.257 inches. But then it says to round to the nearest 1/4 inch. And because, well, technically the nearest 1/4 inch is 2.250, but we can't go down. So then we'd have to round up. So our real answer, rounding to the nearest 1/4 inch, would be 2.50 inches. And that would be the minimum required diameter for bar AB. Right. So that's our answer. 2.50 inches. And then we can move on to the next problem. This problem, which is RB. If I draw it here, you can see. So we have an support here, and roller support. Just see. Roller support, and we have our distributed load, which is 4 kilonewton meter. And then we have a moment here, 1 kilonewton meter, and then point A, point B. So this length, this length is 7 meters, and this length is 4 meters. And then if we have a zoom in on our pin, it would look something like this. Which we have a force here, and then we have two V's. V forces here because of it being a double shear. So these are two shear forces. So we can add our forces as our free body diagram. So because this is a pin right here, we can add, we can add AX and then AY. And then this one's only a roller, so we can say that this is BX. And then we could solve for our distributed force and make it a single force. So for that, we draw a line down the middle. And then because this is 4 kilonewtons over meters, and this is 7 meters long, we would have to multiply this times this. So meters times meters, or meters over meters would cancel, leaving only kilonewtons. So 7 times 4 is 28. So this is 28 kilonewtons. So from that we can ignore our distributed load. So based on the reaction forces at A, determine the required diameter D of the bolt. So we can solve for our, or we need to find AY, which is gonna be this force right here. So we have, or we can use our equilibrium equations to find that. So we can start by doing moment of A equals 0 in the counterclockwise direction. I chose A because of our two forces here, so we can just ignore those. So this force right here will make our beam rotate, but clockwise, so that would be negative, right? Because we decided that counterclockwise would be positive. So we have 28 kilonewtons force, which we multiplied by the distance A from this force. And because this entire distributed force is 7 meters, we need half of that, right? So that is 3.5 meters. And then we have, oh, that is so my bad. We don't have this force right here. It is By. Sorry, that was confusing. So because we have By here, we have, if this were pushing upward, this would make our beam rotate this way, clockwise or counterclockwise, and that would be positive, right? So positive force By multiplied by the distance from A to B. So that is 7 plus 4, which is 11 meters. And that is it for our moment of A. So we can isolate By and then solve for that. So when we isolate By, then we get By is equal to 8.91 kilonewtons. And now we can solve for our other equilibrium equation, Fy equals 0, because now we have By. So we have Ay missing, so Ay minus 28 kilonewtons, because it's our other vertical force, plus By 8.91 kilonewtons equals 0. So from this, we can isolate Ay, and solving for this, we receive Ay is equal to 19.09 kilonewtons. So Ay is this right here. So because of that, we have our two shear forces. So V would be F over 2, right? Because for this to be an equilibrium, two of these need to equal this. So V would equal to 19.09 over 2, which I got 9, or V is equal to 9.545 kilonewtons. So that is V right here. So this is 9.545, this is 9.545.
So we have given factor of safety is 3 and the ultimate stress is 200 megapascals. We have our V force, or our shear stress that we just solved for, or in other words it'd be 9,545 newtons. So factor of safety, we could say that it's the allowable stress over the actual stress. So we're already given the ultimate stress here. So that's 200 megapascals over our actual stress, which is V over A for our area. So our area is not provided, so that's what we're solving for. So we could plug everything in. So that's factor of safety 3, which is equal to 200 megapascals over 9,545 newtons over area, which will be pi over 4 diameter squared. So then we can just isolate D, and when we solve for D, we get D for diameter is equal to 13.5, and then newtons over millimeter squared is megapascals, so our diameter would be in terms of millimeters. But then it says to round to the nearest millimeter, so we can't round down. So then our final answer would be 14 millimeters for our diameter, given our factor of safety and our ultimate stress. And then finally, for the last problem, asking whether a larger or smaller diameter is required for a single a single shear bolt, we would say that a larger diameter is required because there's greater stress on the single shear, as opposed to like double shear, which could have a smaller diameter since it's supported by 2 shear planes. Okay, so we have our third problem, which is the graph. So part A, I already identified the elastic limit, the yield stress, the ultimate strength, strain, and fracture, and the modulus of elasticity, which we'll need for later. That's E equals stress, and we have 400 megapascals over 0.002 millimeter over millimeter, which is 200,000 megapascals. So that's E, right? And then we need to find, for part C, the longitudinal stress, the strain, and lateral strain due to the applied 20 kilonewton tensile force. So for that, we have stress is equal to the force over area, and we have the area since our diameter D is 10 millimeters, and then we have the 20 kilonewton tensile force. So 20 kilonewtons would go here, and then the area would go here. So that would be 20 kilonewtons, which is the tensile force. And then we have area, which is pi over 4 times the diameter, which is 10 millimeters squared. And then solving that, we get 0.225 kilonewtons over millimeters squared. So if we want it in megapascals, we can convert kilonewtons to newtons. So to do that, we'd have to multiply by 1,000. So that's 225, or 2, 1, 2, 3, oh yeah. So that's 225 newtons over millimeter squared,
which is the same as megapascals. So that's 225 megapascals for part B, or sorry, part C. So this is the longitudinal stress. So now we can move on, and then we can find longitudinal strain. So strain, we can use Hooke's law, which we have right here. So E equals stress over strain. So we have our E, which is 200,000 megapascals. And then now, since we just solved for it, we have our stress, which is 225 megapascals. So we can use these two to solve for our missing variable. So we can move this around. So we have this equals stress over our modulus of elasticity. So this would be 225 megapascals over E, which is 200,000 megapascals. So that would simplify, and we would receive 0.00112 0.001125, and this would cancel, so it would be unitless. But because we're already using millimeters over millimeters, you can just put millimeters over millimeters. So that is our longitudinal strain. And finally, we're going to solve for our lateral strain. So with lateral strain, we can use our Poisson ratio. So we would have negative the Poisson ratio multiplied by the longitudinal longitudinal strain, which would equal our lateral strain. So we can just plug everything in, and because the Poisson ratio is already provided, it's negative 0.35, and then we just got our longitudinal strain, so multiplied by 0.001125 to receive our lateral strain, which is negative 0.003937. And once again, because this is millimeter over millimeter, sorry, I forgot to put the units. This is millimeter over millimeter, so this is also millimeter over millimeter. So here we have our stress, and then we have our longitudinal strain, and we have our lateral strain. So I think there's one more part of the problem. I was missing modulus of resistance. So to find modulus of resistance, we have a specific equation for that. I'll move over here. We have a specific equation for that. So modulus of resistance equals stress squared over 2 times our modulus of elasticity. So we can literally just plug everything in. So we have our stress right here, which we solved for. Or sorry, hold on. This is supposed to be our yield stress, I apologize. This is our yield stress, and as we identified in the graph, our yield stress would be 400 megapascals. So it would not be this one right here, because it's longitudinal stress. This is yield stress. So we can go ahead and plug this in to solve for our modulus of resistance. So we have 400 megapascals, which we identified in the graph. 400 megapascals squared all over 2 times 200 megapascals. 200,000 megapascals. Did I say 200? 1,000 megapascals. So this is our modulus of resilience. And then solving for that, we get 0.4. This is megapascal squared, and this is megapascal. So when we cancel, which leaves megapascals on top. So this is 0.4 megapascals. And then we have one more part to the problem, which is finding our maximum tensile force that the material can resist. So we have our ultimate strength, which we showed in our graph, which is the very peak of our Y value, which is stress. So as we showed in the graph, that would be 500 megapascals. And then, so we can use our stress equals force over area equation, because we have our ultimate strain. And then we also have our area, which we found earlier here, which is pi over 4 10 millimeters squared. But what we're missing is P, which we can solve for using these two. So we can get 500,000 megapascals equals P, which we're missing, over area. So we have pi over 4 10 millimeters squared. So that's our area. So using this, we can solve for P, which would be our maximum tensile force. It's getting kind of confusing. So when solving for that, when we isolate P by multiplying pi over 4 times 10 millimeters squared by both sides, we isolate P, and then for P we would receive P is equal to 39,269.908 megapascals over millimeter squared. That would leave newtons. So this would be in terms of newtons. So yeah, because newtons over millimeter squared is megapascal. So that means our maximum tensile force is in newtons. But actually, in the problem it says kilonewtons. So if we wanted to change this to kilonewtons, we would move our decimal place 3 spaces to the left, which would be 39.27 kilonewtons. So that is our maximum tensile force. And that's it for this problem. Okay, finally, we have our last problem, which is the rigid beam and the steel cable.
So if I draw right here, here's our beam. We have A, B, C, D, which has a pin support, excuse me. And then here we have our steel cable, BE. And then E goes up here. And then we have our distributed force, which goes from B to C. So distributed force, and that's 2 kips per feet. So, and then I can add our lengths down here. This is 4 feet, this is 10 feet, and this is another 10 feet. And then this length is 12 feet. 12 feet. Yeah. So, I think I'm supposed to work out the whole problem. So, no problem. We can draw our forces on our free diagram here. So we would have, because this is a pin right here and right here, we can add our X and Y forces. So we have EX and then EY, and then we have DX and then DY. So those are our 2 forces. And then we can draw our expected kinematics right now. I'll draw it in a new thing, but then if our force right here is pushing downwards, we can probably assume that our beam is probably going to tilt like this way. So our expected kinematics, we can, if this is A, B, C, D, we can probably draw it like this. So this is our beam going from this to this because of our force. So we can turn this into a triangle, and this would be our new points. So we have A prime, B prime, C prime, and D prime. Oh, sorry, wait. Because this is a pin right here, it won't go any lower than where D is, so there would be no D prime. So D stays, and then we go like that. And then now we can write our displacements. So this line right here, the distance from A original to A prime, is the displacement of it. So we have displacement of A, and then displacement of B, and then displacement of C. And then we can, I guess we can still draw our other forces. So this is our force B to E. And then we have our D forces. So D, oops, I didn't even know this. Apologies. This is DX and this is DY. DX. Excuse me. And then we also can draw our normal force at BE. So if we isolate this and then we make a cut, actually, we can do this in a second. But then first, we can do our equilibrium equations to find this force at force of BE, right? So first of all, I keep saying first, we can do moment. So we can do a moment equation. And if I had to choose, we can choose B. Because, well, it doesn't matter. So moment of B is equal to 0. So we can see whatever moves our B, right? So D of X, it won't do anything because
it would be pushing towards B and it won't rotate it at all. But then we have dy, which would rotate our, let me make this positive. So counterclockwise positive. We have our dy, which would rotate our B this way, which is counterclockwise. And we already established that our moment counterclockwise would be positive, right? So we can find the distance, or well, we can put dy first. So the force, which we multiply by the distance from B to D, which 10 feet plus 10 feet is 20 feet, that's 20 feet. And then we also have our distributed load, which will also make our beam rotate. But in this case, because it's going downwards like this, it's gonna make our moment rotate clockwise, right? So in this case, it would be negative. So we can modify this. So instead of a distributed load, we can do a single force right here. And for that, we would multiply 2 kips per feet times 10 feet. Because of if it's 2 kips for the entire length and it's 10 feet, then we have to multiply those. So feet over feet would cancel, which leaves only kips. So that'd be 10 times 2, which is 20. So we have our single force right here, 20 kip. So we can ignore this distributed force. So now we can do minus, and then we have our 20 kip force, and then we need to multiply it by the distance from B to this point. So that would be half of 10 feet. Right, because it's right in the middle. So we would multiply 20 kip times 5 feet. And that's all the forces that are going to make our beam rotate. So we can set this equal to 0 because it's an equilibrium. So solving for dy, I got 5 kip. So that's one thing. So now, because we have our dy, we can use our second equilibrium equation for forces in y, right? So we have dy going upwards, so we have 5 kip here, minus 20 kip, because this is a downward force. And then we also have our force BE, which I have pointing upwards, so we can do plus force BE equals 0. So solving for force BE, we get positive 15 kip. So that's how we got this force. And then from this, we can draw our normal forces inside cable BE. So if we made a cut right here in the middle, we can draw this right here. So we have our upward force, force BE that we just found. So that's 15 kip. And because we made a cut right here, we have our normal force. Well, technically, we could say that our normal force is like this, so that it's in equilibrium, or our vertical forces are in equilibrium, but usually normal would go upwards like this. And then I can just draw a V, I guess, and then a moment. So with this, we can solve for n because we have our vertical force here. So if we use Fy equals 0 again, we have 15 kip. And then minus our normal force equals 0. And then we get 15 kip equals n. So this is also 15 kip because it'd be in equilibrium. That's positive. So now we can finally compute the change in length of the cable. Use modulus of elasticity equals 29,000 KSI. I think I have enough space. I guess I can write like this. So we're trying to find change in length BE, and then we would use the equation that we have, which is the force times the length multiplied by area times our modulus of elasticity, which is provided in the equation, or provided in the problem. So we already have our force, or I guess this is the n, sorry. We already have our n force, and then we also have the length, which if we were to convert it to inches, we have our length of 12, which is the same as 12 times 12, which is 144 inches. So we'd be using that for this equation. And then we have our area 2, which is also provided in the problem. That's A equals 2 inches squared. And then we have, as I said, our modulus of elasticity. So we can just plug everything in to find our change in length. So we have 15 kip multiplied by what we said here, 144 inches. And then our area, which is 2 inches squared. And then finally our modulus of elasticity, E, which is 29,000 KSI. And KSI is the same as kip over inches squared, which is why we have inches up here too. So inches and inches would cancel, and then kip and kip would cancel, which leaves only inches, which makes sense because a change in length would be in terms of inches, right? So that is 0.0372 inches, or we could say 3.72 times 10 to the negative 2 inches. So either or. So that is what this is. That is our change in length of BE, right? Because when our bar, when our bar goes from this to this, this length, BE, would have to increase, right? Because it's stretching to down here. And that is what this is. So I think there's one more part to this problem. Determine the consequent vertical displacement at point A. Okay, yeah, so for that, we can use the triangle method. So this is the displacement at A, and then right there is the displacement of B, right here. So this length is 0.03724 inches, right? Okay, yeah. And we have this entire length right here So like we could say that this is one whole triangle. Well, actually, yeah. We could say that this is one whole triangle, and then one side is displacement of A, and then the other side is this entire length, which is 4 plus 10 plus 10, which is 24 feet. And then we have our smaller triangle on the inside, which you already have this displacement for, which is 0.03724 inches. So we have this, and we have this length right here, which is 10 feet plus 10 feet, which is 20 feet, right? So using our triangle method, we could say displacement of A is equal to, or displacement of A over this length, which if we convert it to inches, is 288 inches, is equal to the change in length, BE, or the displacement of B. It's the same thing. And then this would be over this length right here, this length, which 10 feet plus 10 feet is equal to 20 feet. 20 feet times 12 is 240 inches. So we already know what B is, so we just have to solve for A. And then when we solve for A, I get displacement of A is equal to 4.464 times 10 to the negative 2 inches. Yay! And then that's it for this problem, right? So we have this, and because it's in double shear, we would have to multiply A times 2, because that's the equation for double shear. So we have 9.545, or sorry. So we have our given ultimate shear stress, which is 200 megapascals, is equal to what we just solved for. V equals 9.545 kilonewtons times 2, and then area. And like in our previous problem, we have, I think in our previous problem, in our other problem, we can use these two these two values to solve for our missing value. So area, pi over 4, diameter squared, and then millimeter squared. We can actually convert our kilonewtons right here to newtons. Since megapascals is the same as newtons over millimeter squared, we can convert this to newtons, so it'd be newtons over millimeter squared, which would equal megapascals. So this in kilonewtons would convert to this in newtons. So 9,545 newtons. So we have this right here, and then we can solve for our missing D. So 9. And with that, I get D is equal to 5.512. Millimeters. And yeah, I think that's what it is. And actually, when we round to the, oh my gosh, you can't even see. When we round to the nearest millimeter, this actually isn't even, when we round, that is 6. So D is equal to 6 millimeters. I think that's right. Yep, okay.